Let's look at a projectile motion that involves a projectile that is, instead of being launched upward from the surface of the Earth, is launched downward from a point that's above the surface of the Earth. And that's this snowball problem. A snowball rolls off of a roof, leaves the roof at an angle. If I extend these lines a little bit, you can see this is the direction of V naught, and it makes a 40.2 degree angle with the horizontal there. So that's the situation. Now, still projectile motion. I'm going to write the projectile motion equations as if, well, like we always do. V naught x will equal V naught cosine theta. V naught y will equal V naught sine theta. X equals x naught plus V naught xt. By the way, you should be getting to the point where you can write these down from memory or know that you want to copy them from the formula sheet. And you should have copied enough of these from the formula sheet that you're getting pretty good at it. Also, we'll have y equals y naught plus V naught y t minus 1/2 gt squared. Okay, so there's the equations we work with every time. Something I'd like you to do is to pause the recording right now and figure out what the values of V naught x and V naught y happen to be. So go ahead and pause the playback. All right, hopefully you have that done. I'm going to show you how I figured them out. I just draw this picture here, redraw this picture, and make a little right triangle here. It's got V naught y pointing down, V naught x that way, and this is the angle 40.2 degrees. And the magnitude of V naught, 3.98 meters per second. It's on the diagram, or on the drawing. Now, I know V naught y is going to be negative, and so I'm just going to write it with the minus sign. V naught y is going to be minus this thing, V naught, times the cosine of 40.2 degrees. And I don't care that this is a negative angle. I know the direction of V naught y, it's down. So minus 3.98 meters per second cosine of 40.2 degrees, which is minus 2.57 meters per second. V naught x similarly will equal just V naught, whoops, V naught y was the sign. Excuse me, hope I didn't confuse you too much. V naught cos theta, which is 3.98 meters per second cos of 40.2 degrees. And V naught x ends up being 3.04 meters per second. Okay. One other way we can initialize this problem is to assign an origin and pick the initial values of V naught x and V naught y. I'm going to put the origin right here, directly above or at the point where the snowball leaves the roof and straight up from the origin. Okay. With that choice, x naught will equal 0, and the snowball starts 14.1 meters above that point, so y naught is 14.1 meters, and I'll transfer those values over to here. Now let's look at what they're going to ask me. Let's see, ignore air resistance. All right, how far from the edge of the barn does the snowball strike the ground if it doesn't strike anything else while falling. How far from the edge of the barn? That's going to be in the x direction. So I'll eventually be solving this equation. Now, with x not being 0, the x equation just becomes v naught x t. But I need to know how long it's in the air. Think about this. Pause the recording and think, how could I determine how long this thing is in the air? So do a recording pause and go for that. Hopefully you decided that the y equation could be solved to give you that time. Y naught is 14.1 meters. When it strikes the ground, y will be 0. And so the y equation, y naught, I'm going to copy it again. Get in the habit of writing these things down. In this case, it will equal 14.1 meters. Now, v naught, whoops, this is v naught y, is the negative one, minus 2.57 meters times t, minus 1/2 times 9.81 meters per second squared times t squared, and it's going to equal 0 when it strikes the ground. So I have a quadratic equation here in t, and it'll give me solutions. Now, I solved this on my calculator. Today, I'm actually using this one that has the program I wrote for solving quadratic equations. If you have a TI-84, you should be able to connect it to your computer via the USB port on the side and download programs to it. Look up on YouTube how to do that. There's a quadratic equation solver. Or, if you like programming, you can read about how to program this and write a program that does quadratic equations. It's a nice little exercise. When I do that, I get two solutions to this. I get t equals minus 1.978 seconds, or t is equal to 1.45 seconds. Okay. Negative answer? Not in this case, but let me make a quick sketch. Let me make a quick sketch and show you where that comes from. We have level ground here. If we had a projectile launched in the air such that at one point in that projectile's life, it had a 14.1 meter high elevation above the ground. It had a velocity at that instant that made a 40.2 degree angle below the horizontal, with a speed at that instant of v equals 3.98 meters per second. And we decided for some reason to define this as the zero of time. Okay, so here was our time axis, and this would be y in meters, and this would be t in seconds. This would be minus 1.98 seconds. Is what that thing happened to be. Whoops, I wrote too many significant figures there. So anyway, that's what that negative root means. But this projectile didn't do that. It rolled off the hill, so this is all fictitious stuff. Now we can move on from there. We don't need that negative root. T equals 1.45 seconds, and we can figure out how far from the base of the building it lands. So x equals v naught x, which is 3.04 meters per second. I don't like to do that where I start off with numbers. I want to remind myself it's v naught x times t. 4.41 meters from the base of the building. Now if I look at this thing, This person is standing over here only 4.05 meters from the base of the building. 4.41 meters is, let's see, that's only 36 centimeters. Well, it's a little more than a foot past this person, a foot and a few inches. That'll be exciting. Actually, here's how long it happens to be. Clears their head, or clears their feet by about that much. So that's how far from the base of the building it happens to land. Well, the next question says a man 1.90 meters tall, that's this fellow, is standing 4.05 meters from the edge of the barn. Will he be hit by the snowball? Stop and think about how you might be able to figure that out. We've got some equations here. Which one might you use for that? So pause the recording and see if you can figure that out. Just how we'll do it. I'm back. Let's figure that out. Now, we want to know if when the snowball gets to this position, 4.05 meters, how high is it? Well, how long does it take to get to that position, to move sideways 4.05 meters? That's the x equation. So we know that x is equal to v naught xt. We want to know the time. Now I'm working sideways on a single line. I don't want you doing that on your homeworks. But we want to know the time when x happens to have that value of 4.05 meters. So 4.05 meters divided by v naught x, 3.04 meters per second. And how long is that? 1.33 seconds. Okay, this thing hits the ground after 1.45 seconds. This is only 12 hundredths of a second before then. Okay, things are going to get kind of dicey here. We'll find out just how bad. Well, let's figure out, now we know how long it takes to be at that location, which is somewhere between this point and the ground. Let's find out how high it is at that time. That's the y equation. Y at that time will be y naught plus v naught y t minus 1/2 gt squared. And yes, I know v naught y is negative. That's going to show up here. So we'll have 14.1 meters minus the y velocity, 2.57 meters per second, times 1.33 seconds minus 1/2 times 9.81 meters per second squared, units everywhere, 1.33 seconds squared. And plugging in all the numbers, I get that at that time, y is 2.01 meters. Holy smoke, this guy is 1.90 meters. If I subtract that from here, it's only 0.11 meters above the man's head. Okay, how high is that? Well, this is 0.11 meters right between here. It's about a little over 4 inches. So this guy's going to feel this snowball whistling past his head when that happens. Okay, how exciting for him. The last part of the question asks you to make x versus t, y versus t, v sub x versus t, and v sub y versus t diagrams for the motion in part A. And I've already just sketched some sort of blank graphs here. On all of them I put a point at 1.45 seconds, since that's the time that it spins in the air. And let's see what happens. Well, x versus t, remember that's described by x equals v naught xt. Okay, this is the t-axis in seconds. Well, that's just a straight line, and it's got a slope of v naught x, no vertical intercept. It goes through the origin. So if I just draw a straight line with a positive slope, there we go. Slope equals v naught x, which I have on another piece of paper, somewhere here, 3.04 meters per second. Now, the y versus t graph is not so simple. We've got y is equal to 14.1 meters per second. Oh, I'm going to run out of room with that. Minus that 2.57 meters per second times t, minus 1/2 times 9.81 meters per second squared t squared. Okay, this is the graph of a parabola. Okay, when t is 0, it's got a particular value up here, and 14.1 meters per second, it's up here, or meters, that's just meters for the position. All right, and it's actually got a negative slope to start with, but because I put that so far out here, I have to give it a barely negative slope. And the slope at time 0 is the 2.57 meters per second, but it gets steadily more negative as time goes by. And so I couldn't draw that very well, but this is actually a curve getting steeper. And so that's the way the y versus t graph. If I'd had a shorter time on here, but I wanted to show them all being the same, it would look more like something like that. So, but that's not correct for the value that I put on there. Then a v sub x versus t graph. What's that going to look like? Well, v sub x, it's constant. It's always 3.04 meters per second. And that would be the units on this graph. And it stays the same until it hits the ground. So, let's see. And we're not going to try to figure out what it did after it hits the ground. It'll probably bounce a little bit and keep going somehow, but it's definitely not going to stay constant. Okay, and then the v sub y versus t. What's that graph going to look like? Well, it starts off negative. If I write down v sub y, it's going to equal v naught y minus gt. We didn't bother to figure out how fast it was going when it hit the ground, but its initial value is minus 2.57 meters per second. So that's where we'll start. And then it gets more and more negative as time goes by. So minus 2.57 meters per second minus gt. And the slope of this graph will be g. So that's what it does. Oh, and when it hits the ground, it absolutely stops. So those are those graphs. And nice to be able to reason through these things. So you might try doing that for some of the other projectile motion problems. Okay, that's the last projectile motion problem I'm going to do. We'll call it good.